Hello students, welcome to 7th lecture of Chemical Bonding and Molecular Structure. In previous lecture, we were discussing about the parameters of bonds. So, few of them are already covered and let us start with remaining ones. So, our next point is the resonance structure. It is observed that the single Lewis structure is inadequate with the representation of molecule in conformity with its experimental determined parameters. For example, when ozone O3 molecule can be equally represented as the structure 1 and 2. That means, as we can see, we have two different structures of ozone. Suppose let us say this is our first oxygen, this is second, and this is third. So initially we have single bond between first and second oxygen and double bond in second and third oxygen. Similarly here, as we can see in second structure, between first and second we have double bond, between second and third we have only a single bond. So both of this structure can be summed up as follows. So as we can see, we have a uniformly distribution of bonds in all of these three oxygen, and bond lengths are less than single bond but more than double bond. As you can see here, the single bond length is 148 and the double bond length is 121, and here we have 128 pm of a bond length. That means less than single bond, more than double bond. So in both structure we have oxygen oxygen single and double bonds. Normal single and double bond lengths are 148 121. Experimentally determined oxygen oxygen bond length is 128 in O3. Okay, so keep in mind, single bond length usually it is 148, double bond length is 121, but here in ozone each and every bond, that means bond between first and second and third oxygens, they are 128. That means they are exactly same. Okay, first and second both type of bonds are same, and lengths are also the same. Thus the oxygen oxygen bond in ozone molecule are intermediate between double and single bond. Obviously these cannot be represented by either of two Lewis structures shown above. So we cannot represent partial bond between two atoms using Lewis structure, because this bond shows that they are in between. That means they are not single bond or not double bond. They are between single and double bond. That's why bond length is between the length of single bond and double bond. So we cannot represent this type of partial bondings using Lewis structure. So that's why the concept of resonance is introduced to explain the molecular structure like O3 molecule. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy positions of nuclei, bonding and non-bonding pair of electrons are taken as the canonical structure of the hybrid, which describes the molecule accurately. Okay, that means first we will try to find different type of structures, different type of possibilities, and then we will mix those possibilities with each other to create some good explanation about the structure of molecule. As you can see in this example, we have two different type of structures of ozone, and after the sum up of both of these two, we can end up at this third structure, which can explain the structure of ozone. So in O3, first and second structure are canonical structure, and hybrid of those two structures will be the third structure, as we already saw. So this is also called resonance hybrid. Resonance is represented by double headed arrows. Now let us try to understand the structure of carbonate and carbon dioxide molecule. So our problem is explain the structure of CO32 minus ion in term of resonance. So we already discussed about the structure, Lewis dot structure of CO3 minus in previous points, but in this case when we compare those structure with practically observed data, then they do not match. That means in a normal structure representation, of CO3 minus, one of the oxygen has double bonded structure with carbon and remaining two oxygens are single bonded. But in case of practical data, you can see that all of the three bonds are equivalent. That means their bond lengths and nature, they are exactly same. So they must show resonance structure. And to represent that resonance structure, first of all, you have to find all the possible structures of that molecule or ion. As we can see, we have these three possible structures or outcomes using Lewis dot structure. That means all you have to do is place a carbon, arrange oxygen around it, and step by step, as we can see, in first case we have double bond with first oxygen and single bonds with second and third oxygens. Then this double bond will be cancelled out and bond will be shifted towards the second. Then again bond will shift towards the third oxygen. So overall we have these three structures, and as we can see, practically observed data suggests all of these three bonds are same in nature. They are equivalent, energies, lengths, all of that parameters are same. So which of them will be true? And which structure should we select? So answer is all of these three structures are true. And this type of continuous situation is being observed in CO3 minus ion. Or you can represent the resonance hybrid of this molecule as like this. Okay, all of these oxygen contains permanent single bond, and the second bond will be distributed in all of these three oxygens equally. That means we can predict like this. We have total one oxygen contains double bond with carbon and two oxygen contains single bond with carbon. That means total number of bonds will be 4. So we have 4 bonds and number of atoms, that means number of oxygen, it will be 3. Okay, so this will be the portion of the bond for each oxygen, 4 by 3 or 1.33. Okay, this will be the bond order of oxygen in CO3 minus. Next problem is about CO2 molecule. So experimentally determined carbon to oxygen bond length in CO2 is 150. The length of the normal carbon to oxygen double bond C double bond O and carbon to oxygen triple bond C triple bond O is 121 and 110. That means in case of carbon dioxide, bond length is between double and triple bond. It is comparatively shorter than double bond but longer than triple bond. So this value lies between the double and triple bond, and obviously single Lewis structure cannot depict this position, and it becomes necessary to write the more than one Lewis structure and to consider that the structure of CO is best described as a hybrid of canonical or resonance form. So here we have structures. So as we can see in first case, it looks comparatively normal. Now notice here between carbon and oxygen we have total 4 electrons. So actually it represents double bonded structure. And this will be the second oxygen, not the carbon. So with the second oxygen, as you can see, we have 4 electrons. That means again double bonded structure. So this is our first canonical structure. Then second structure suggests that oxygen, first oxygen is negative ion and it has fully filled orbitals and it do not share anything with carbon, but it is negative in charge. On the other hand, second structure or second part suggests between carbon and oxygen we have total 6 shared electron or triple bonded structure, and this oxygen will be positive in charge. So we can say that we have negatively charged oxygen and positively charged CO, and they are attached with each other using covalent bond. And similarly, third structure represents the same thing but opposite. That means between first oxygen and carbon you will see triple bonded structure and positive charge, and second oxygen will be negative. Okay, and they will feel covalent electrovalent attraction. In general, it may be stated as resonance stabilizes the molecule as the energy of a resonance hybrid is less than the energy of any single canonical structure, and resonance averages the bond characteristics as a whole. That means, as we discussed, in case of CO3 we have total 4 bonds and 3 oxygen, so we have to divide 4 bonds in 3 oxygen. Thus, the energy of O3 resonance hybrid is lower than the either of the two canonical forms, figure 1 and 2, as mentioned previously. Now, some misconceptions are also present about the resonating structures. So, remember that the canonical forms have no real existence. So, canonical forms are actually representation how all of this system works. Okay. The molecule does not exist for certain fraction of time in one canonical form and for other fraction of time in other canonical form. That means these structures are not interchanging into each other. There is no such equilibrium between the canonical forms as we have between the tautomeric forms, keto and enol, and the molecules as such has single structure, which is the resonance hybrid of canonical forms and which cannot as such be depicted by the single Lewis structure. Okay, so these are some clarifications about the misconception. Now let us move on our next point, polarity of bonds. So in simple term, what we can say about the polarity? So poles, that means ends. Okay, anything which has ends we can call it poles. Just like South Pole and North Pole, these are the two ends of Earth. Similarly, molecules also carries two different type of ends. Certain molecules, not all of them. If two different atoms combines with each other to form a covalent bond, then there will be some polarity depending on that difference of electronegativity. Okay, we can understand these points using example more easily. So let us start the point. The existence of 100% ionic or covalent bond represents an ideal situation. That means in reality we do not have 100% covalent or ionic bonds. Even in case of the covalent bond between two hydrogen atoms, there is some ionic character. So when the covalent bond is formed between two similar atoms, for example H2O2, Cl2, N2F2, etc., the shared pair of electron is equal attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. Suppose we have a hydrogen having one single electron and second hydrogen having another single electron. So when this hydrogen forms bond with each other, they will share one electron of each. Now as we know, electronegativity actually represents the electron attraction. Higher the electronegativity, more will be the attraction towards the electron. But in this case we have same type of element. Both type of elements has exactly the same electronegativity. That means both will attract electrons equally. So because of equal attraction, this electron pair will remain at the center of the molecule. Similar type of situation will be seen in case of Cl2. In case of chlorine, we have two different chlorines having one single electron. When these two chlorine form bond with each other, their electron pair, shared electron pair, will be at the exactly center. But what happened when H and Cl combines? Both of them has different type of electronegativity. Chlorine is more electronegative than the hydrogen. That means chlorine attracts electrons strongly. So in this bond formation, one electron actually belongs to chlorine, second electron belongs to hydrogen, and this will be the center of molecule. But because of less electronegativity of hydrogen, it attracts electrons weakly. But stronger electronegativity of chlorine shows that it will attract electrons strongly.
So that's why shared electron pair will be closer to chlorine and it will be away from the hydrogen. So electron of hydrogen is away from hydrogen. That means now it will gain some positive charge. It is not permanent positive. That's why we have to place delta sign before it, which represents partial positivity. Okay, so delta, that means partial, which is not equal to 100%. It will be less than 100%. Okay, if it carries 100% charge, then we can call it ion, but it is not 100%. It is not neutral. It is positive than neutral, but not 100% positive. Similarly, shared electron pair is closer to the chlorine. That means negativity of chlorine will increase. But this electron is not completely shifted into chlorine. That's why it is not permanent negative ion, but instead it is partially negative. Okay, it is not 100% negative, but it has some negative charge on it, and it is because of uneven distribution of shared pair. And why this uneven distribution occurs? Because of difference in electronegativity.
So when same type of elements combines to form a molecule, they forms non-polar bond because they have exactly same charge. None of them carries positive or negative charges. So it is called non-polar covalent bond. Contrary to this, in case of the heterogeneous heteronuclear molecule like HF, as we discussed about the HCl, the shared electron pair between two atoms gets displaced more towards the fluorine since the electronegativity of fluorine is far greater than that of the hydrogen. So electron pair will be closer to the fluorine and it will be away from the hydrogen. That's why hydrogen gains partial positive charge because electron of hydrogen is moved away from the hydrogen. But it is not completely removed. If it is completely removed, then hydrogen will become ion. So it is still in contact with hydrogen, but distance is increased. So the resultant covalent bond is polar covalent bond. When these type of uneven distribution of shared electron pair occurs, it gives us polar bonds. As a result of polarization, the molecule possesses dipole moment, which can be defined as the product of the magnitude of the charge and the distance between the centers of positive and negative charges. It is usually designated by a Greek letter mu. Mathematically, it is expressed as follow. So it is equal to charge multiplied by distance of separation r. Dipole moment is usually expressed in dBi unit, and 1 dBi is equal to 3.33 into 10 raised to minus 30 coulomb per meter. Further, dipole moment is a vector quantity and is depicted by the small arrow with the tail and on the positive center and head pointing towards the negative center, which represents electrons are attracted towards the negative center or more electronegative element. So in case of HF, we can represent it like this. Arrow will start from hydrogen and it will go towards the fluorine, which represents electrons are more attracted towards the fluorine. The shift of electron density is symbolized by the crossed arrow above the Lewis structure to indicate the direction of the shift. In case of polyatomic molecule, the dipole moment not only depends upon the individual dipole moments of the bonds known as bond dipoles, but also on the spatial arrangement of various bonds in the molecule. In such cases, the dipole moment of molecule is vector. Sum of the dipole moments of various bonds. For example, in H2O molecule, which has a band structure, the two OH bonds are oriented at the angle of 104.5 degrees. The net dipole moment of 6.17 into 10 raised to minus 30 coulomb per meter is equal to resultant of the dipole moment of two OH bonds. So as we can see here, we have two different hydrogens attached with the oxygen and we have a band structure. So resulting dipole moment will be as discussed here. As the arrow suggests, it will be towards the oxygen, but because of the band structure, it will be slightly different. That means it won't be like this and this, but
effect of both hydrogen will combine and it will result in this direction. Okay, and the net dipole moment is 1.85 d for given molecule. That means 6.17 into 10 raised to minus 13. The dipole moment in case of BeF2 is 0. Although BeF bond is polar, overall dipole moment of BeF2 will be 0. Why? Because it depends on spatial arrangement and the shape of BeF2 is linear. So both of the fluorine will try to attract electron pair towards them. So overall none of them will get any extra electron pairs and you won't get partial positive and partial negative charges, and that's why we cannot call it polar bond. Polar molecule contains two different charges on two different ends, so it is non-polar. So we can say that if a structure is uniformed then it will be non-polar. In tetraatomic molecule, for example BeF3, dipole moment is 0 although the BF bond are oriented at the angle of 120 to one another, and the 3 bond momentum gives the net sum of the 0 as a result of any 2 is equal and opposite to the third. Okay, so again this is a planar structure BF3, planar triangular structure, so all of the fluorine are trying to pull electron pairs toward them. So none of them gets extra, and that's why overall it will become 0. Now let us discuss about the interesting case of NH3 and NF3. Both of the molecules have pyramidal shape with a lone pair of electron on nitrogen. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of NH3 is 4.9 and it is greater than NF3, which is 0.8. And this is because in case of NH3 the orbital dipole due to the lone pair is in the same direction as the resultant dipole moment of NH bonds. But in case of NF3 it will be opposite. So what we are trying to discuss, when nitrogen is attached with 3 hydrogen it will be something like this. Okay, it is pyramidal structure, triangular pyramidal structure, and base contains hydrogen and top will be nitrogen. In this bond formation nitrogen still has a lone pair of electron. As we know, electronic configuration of nitrogen is 2p2 2p3. That means 3 hydrogens will be attached in 2p orbital, but we still have 2s, not 2p, sorry, 2s orbital which has a lone pair of electron. So as we know nitrogen is more electronegative than hydrogen, so electrons will shift towards the hydrogen in all of these three bonds, and we have an electron pair present on the top of the nitrogen, so it also pushes electronegativity or dipole moment towards the top, and that's why this molecule is strong polar molecule. So why NF3 contains exactly same structure? It has exact same structure just like NH3. Then why dipole moment of NF3 is low? So reason is, as we know, nitrogen is less electronegative than fluorine. That means in this time direction of electron will be towards the bottom, and this electron pair is trying to push negativity towards the top. So now we have two different factors acting against each other, and that's why overall dipole moment will decrease. So same is mentioned here. As we can see, this is the lone pair of nitrogen which is trying to pull negativity towards the top. In case of hydrogen, all of the hydrogen also supports this direction, but in case of NF3, electron pair on nitrogen trying to pull negativity towards the top, but more electronegative fluorines are trying to push negativity towards the bottom, and they are opposing each other, and that's why dipole moment of NF3 is less than NH3. Now the dipole moments of some molecules are shown in table 4.5. If you find any difficulty till this point, feel free to ask. You are welcome to ask the question.
and we will meet in next lecture.